So I'm Zahid Irfan, and my work is evaluating fairness metrics, and this was done by me, Dr. Fergal, and Dr. Roisin, and I'm from DKIT. So we start off with the binary classification problem. So we have two classes. We call them positive and a negative class, and there's no bias of calling them positive or negative. It's just a label associated so that we can identify them. And then there's a training algorithm that trains the model, and then we can determine a threshold which can tell us whether a unseen class belongs to a positive class or a negative class. So once we have established a model, then what happens is it brings in some bias. So biases lead to unfairness, and there are two kinds of statistics fairness. Number one is the protected groups need to be ensured that they have equalized influence, like error rate, and this is called the statistical fairness. And then we have another kind of fairness, which means that individual fairness, we would like to say that it is a fair metric where the individuals are treated similarly. Similar individuals should be treated similarly. Now, when we talk about our groups, there are two kinds of groups. One is called the protected group, which is the unprivileged group. And this is the group that is being mistreated because of the bias in the system. And the privileged group is the one that is at an advantage, or at least it is not being mistreated. And so fairness matrices are the metrics which help us determine whether a machine learning system is fair or not. And there are different metrics. For example, demographic fairness metrics. There are two which are similar, but they are the ratios of the positives that are present in the data set. And the second kind of metric is the statistical fairness matrices. One is equalized odds, which say that the true positive rates as well as the true negative rates should be the same for both of the groups, where both of the group means the protected group as well as the unprotected or the privileged group. And equalized opportunity is a simpler statistical fairness matrix, which only deals with the ensuring that both groups have true positive rates that are the same. And the third matrix, which is a bit newer in as compared to the other two, it is the one that ensures that the worst group's error is minimum. It would ensure that if we have many groups, then up from those groups, the one that is the worst group, which is being mistreated, its error is minimized. So these are the three fairness matrices. So the experiment that I performed was based on the German data set, which is a very, very popular and usually it is used, and I use it because it is a familiar data set. So there are two protected attributes in this German credit data set. It's about gathering data of people, and they applied for the credit, and whether they were given credit from the banks or not, that is the risk. So whether they are good risk, this is the target variable, and the rest of variables are age, sex, job, whether they're employed or unemployed, whether they own a house, are they living for free, or they are on a rent, or do they have saving accounts, they have checking accounts, credit amounts, what amount they have applied for, and the duration of how many months do they want the credit for, and the purpose. And so there are two protected attributes. One is the sex, whether the person was male or female, and whether the person was discriminated based on that attribute. And the other is age, and for the purpose of finding the fairness, the people who are older than 25 years are considered to be old for our calculations, and those who are less than 25 are considered young. So it's just a line that had to be drawn, and it turns up pretty good and interesting data results. So when we talk about statistical parity difference, and then if we have zero, if the rates of both are the same, then we'll get a subtraction of that, and that would mean it is zero. And when we talk about disparate impact, that is the ratio of the two groups, the protected and the privileged. And if it is equal to 1, that means we have demographic fairness. As far as equalized opportunity is concerned, if we have a true positive rate, that the number of positives for both the groups in the result, they are the same, then we have equalized opportunity. And ROC is the ROC is the I forgot it, operating curve for operating curve whose, if it is equal to 0, if it is equal to 1, it's better. And area under the curve, if we get higher, it is better, and the closer to 1. And min-max fairness, the one I talked about earlier on, in this we ensure that the model weights are a uniform distribution. So the classifiers that I use are these are also very familiar classifiers, and I use them so that I have a diversity of classifiers of different types. And these are the results. So when I do experiments, I got the age and the sex. They are pretty, so as we remember that the statistical parity difference, that has to be closer to 0, and the disparate impact should be closer to 1 to get a fair classifier. So, and when we talked about equalized opportunity, the results are that for age, the support vector machines and the process, Gaussian process classifier, the Gaussian naive Bayesian, the linear discriminant, for the males and females, as you can see that here, that our Gaussian process classifier is not performing very well. And that would be evident a bit later. And as you can see that the naive Bayesian is performing very, very well. It is equal to 1, which is our best case. And the rest one are also fine, with the support vector classifier performing a little bit better. So here are the ROC curves. And so you see the curves, the area under the curve for the Gaussian naive Bayesian, that is equal to 1. And these are for the sex analysis, meaning that the male and female. And as you can see that when we go to the support vector machines, the operating curve is a bit different for the different thresholds, and its value is not equal to 1, and it's performing very badly for females, and it's a bit better for the males. And while if you use the Gaussian process classifier, this is just a straight line, and when you get a straight line like this, it means that it is as good as a random guess, right? So it is not a very good classifier as far as the fairness. So secondly, for the age, if you look at the age analysis, the results are similar. If you look at both of the graphs, you can see that very little has changed. So that means that our analysis for ROC and area under the curve, they have given us similar results for both the attributes. And then we look at our minimax criteria. Here we only use the logistics. So logistics classifier. And here you can see that for both the attributes, our errors have come down as we have approached to 3,000 iterations. And the sample weights are updated for both the groups, the age group and the sex group. So we see that the results I've already discussed. And so the demographic fairness are not a good idea because they use only the predicted values, not the actual values. Min-max criteria is very good as far as because they minimize the worst groups weights. And the future work is that there is a lot of ground to be covered. because we have to add more data sets so that we can have a better analysis. And minimax criteria needs to be analyzed over across more domains and more data sets so that we can identify its limitations. And that is it. Thank you very much. And I had other slides as well. So receiver operating characteristics, but I did not show them. So these were the, if anybody is interested, that can be available. Thank you.
Is there any question from the audience, either here